Well, welcome everyone to the Geo-Launchpad Summer Research Spotlight. We are very excited to have you all here to learn about what our Geo-Launchpad interns have been up to this summer. My name is Becky McKean, and I am a Geo Workforce Associate 2 at EarthScope Consortium. I am part of the fantastic internship team, and I am also the program lead for the Geo-Launchpad and the Recess programs. You can see other members of the internship team on the slides. We have Kelsey Druce, who's on the call today, Geo Workforce Associate 2, Barbara Reynolds, Community Engagement Coordinator, and Matt Dawson, Engagement Manager. We were also supported this summer by two amazing alumni mentors this year. Our Geo-Launchpad alumni mentor, former Geo-Launchpad intern, Sebastian Griego, who is currently a graduate student at the University of New Mexico, and our Recess alumni mentor, former Recess intern, Elishua Shepard, a graduate student at Purdue University. So a big thanks to the team for all of their hard work and help with Geo-Launchpad. Amazing. Please note some expected behavior for today's event. We will strictly follow EarthScope's Code of Conduct. This means being mindful of providing a safe, productive, and welcoming environment for all participants. We also ask that you kindly remember to stay muted to reduce distractions for our speakers. So a little bit of an introduction as to what Geo-Launchpad is in case you're not familiar with it yet. Geo-Launchpad is a competitive summer internship program specifically for community college students to gain experience in the geosciences. It is an 11-week paid internship that this year ran from May 31st to August 14th. Their last day is tomorrow, which is hard to believe. This year we have 7 interns coming from 4 different states. Students accepted into the program this year began by attending an in-person orientation week at the University of New Mexico in Albuquerque, alongside interns from 2 other EarthScope internship programs. This week included field exercises with technical equipment, professional development seminars, and community building activities. Interns then traveled to their project locations where they have spent the last 10 weeks working on a mentored project and receiving professional development training from EarthScope staff. And along the way, they also receive support from staff and from their alumni mentor, who is Sebastian. This experience will conclude with a poster presentation either at the Geological Society of America GSA Connects conference, which will take place in Denver, Colorado in October, or the American Geophysical Union conference, which will take place in San Francisco, California in December. And all 7 students have already submitted abstracts for these meetings. So where did our interns go this summer? Our interns worked at institutions in 6 states across the U.S. this year, including California, Colorado, Florida, Kansas, New Mexico, and Texas. Their institutions included colleges, universities, and local and federal government agencies. This year, we also worked intentionally to try to pair interns together whenever possible. So before our interns begin their presentations, I would like to acknowledge our funding support, which makes this internship program possible. This program is supported by the National Science Foundation National Geophysical Facility, operated by EarthScope Consortium. I would also like to acknowledge additional support for the program, which you can see listed on the slide there. Our agenda today will include 5-minute presentations from all 7 of our interns. Note that we will proceed directly from one presentation to the next. So please type any questions you have in the chat, and if it's for a specific intern, if you can list their name, that would help us as well. We will hold a brief Q&A following the presentations. But please feel free to use your emoji Zoom reactions for applause after each intern concludes their presentation. Okay, our first presentation will be by Nikodemos Scott from Piedmont, Virginia Community College in Charlottesville, Virginia. Their project was completed under the direction of Dr. Blair Schneider at the Kansas Geological Survey and the University of Kansas in Lawrence, Kansas. Their title is Creating GPR Max Computer Model Simulations for Interpreting Cemetery Ground Penetrating Radar GPR Data in Kansas.
Thank you so much, Becky, for the introduction. Yes, so without further ado, let's dive into Kansas's hidden coffins. So my research focus was looking at 19th century burials and coffins in Kansas. So my location was Valencia County, in Valencia, Kansas, at Valencia Cemetery, which is located in Shawnee County, which is northeastern area of the state. So during the 1800s, you had lots of different people coming together in this one region. So here I'm showing a historic map of Valencia circled in red there. But around you can see other settlements from people coming from the East Coast settling in the area. You had the Oregon Trail going south from people going to the West Coast. You also had Native American tribes all in this one small region. So as all these people were coming together, you had them bringing their cultures intermingling as well. So as they were buried, it could change if they had coffins, if they used fabrics, their directions they had, but it's pretty hard to research because obviously they're all buried. But so we need a tool that can help us investigate all these. Thankfully, we have ground penetrating radar. GPR is a tool that geologists and archaeologists use in order to investigate subsurfaces. So for geology here, you can see as the GPR goes over the surface, it sends electromagnetic waves into the ground, and as those waves interact with anything different than the surrounding areas, it'll send back these readings like so on the left. Here you can see these really distinct geologic regions, but for our purposes in burials, it'll give you more of these parabolas and really targeted areas of focus. So on the right there, you had me and my team, and we were going to the cemetery in Parsons. We were doing field work with the cemetery committee there. And so GPR use in cemeteries and investigating coffins is important because it can help not only with investigating these cultural norms and societal shifts happening, but it can help with preservation and restoration. You can locate lost graves and connect locals with their history. It can also identify burial sites so it can prevent harmful development on top of them. And it can help relatives find their loved ones. So here I'm going to show you two GPR scans from Valencia Cemetery. I want you to see if you can spot the two burials. I'll reveal them to you now. So here you can see on the left this almost cartoon bird shape, like an X. And then on the right you have a pretty wide V shape with an overarching like umbrella. But it's very difficult to distinguish these shapes because it's under the ground and the GPR isn't like an X-ray. So we need another tool that can help us with interpretation. Thankfully, we have one called GPR Max. GPR Max is a computer simulation program invented in 2016, and it can help make simulations of GPR scans. So on the left, I have the Python code that I use to create this model in the center of a coffin as it's collapsing in on itself. So you have soil filling it in the blue with a skull in red, and you have air pockets still in the yellow there. And down below is the resulting B scan or GPR scan that would come from this model above. So since I'm looking at coffins, I made different situations where the coffin is collapsing in on itself. So on the left, I have an intact coffin. In the center, I have that collapsing one. And on the right, I have a coffin where the lid has fully collapsed and the soil has filled in the inside. And so with these coffin scenarios, I put these different body parts into them. Since I'm using 2D scans, I made some parallel and perpendicular to the body. So I have an arm and spine here, a skull, and a femur set. And then I have an arm, a spine and skull, and a leg here. And with these models, you can also get different frequencies. For our purposes, here I have 200 and 400. We use a 200 megahertz frequency to take all of this data. On the left here is what it would typically look like, and on the right you can see that it's much more defined. In real life you would get deeper depths and usually less resolution, but because of Kansas's dense clay soils, we can see a bit more because we're looking only shallowly. So this is a map of confirmed burials from Valencia Cemetery that were confirmed using headstones and GPR data. So without further ado, let's look at some of these and see if we can match and see what they are. So this one is one from 1886, 140 years ago. And these are two scans from models that I invented. And from looking at these, you can see this sharp V shape underneath that matches this one, and this overarching bird shape like here. So this led me to believe that this is a collapsed coffin with a skull buried at 1 meter deep, which model would look like this. And then I have this one here, which was buried in 1994. And this one, I believe, is a decomposing coffin with arms and spine due to this wider V shape with a flat bottom here and here. And that model would look like this. So in the future, we can use this information to make more complex models. We can document these cultural shifts, and we can also work with these communities to help with their conservation. Thank you so much.
Thank you, Nick. Our next presentation is by Alana Jornacion from Allen Hancock College in Santa Maria, California. Alana also did her project under the direction of Dr. Blair Schneider at the Kansas Geological Survey and the University of Kansas in Lawrence, Kansas. Her title is Using GPR Max to Create Numerical Models of No Casket Burials.
Thank you, Becky, for the introduction. So let's get started. Although it may be morbid, I do know one fact, and that is that everybody dies at some point. Humans are very aware of this fact and have been practicing burials for centuries. In my summer project, I focus on the city cemetery in Alma, Kansas. Alma is about 40 minutes westward from Topeka, which is the capital of the state, and here is a map of what the cemetery looks like. I focus mainly on this plot right here highlighted. And you might be asking why this plot specifically. This plot is a potter's field. Potter's fields are usually areas of burials, often like very close together, due to the fact that these people didn't have like a lot of money to buy a burial plot. Either they were unidentifiable or they were unclaimed by family. So these burials often had like no headstones and sometimes were buried with no casket. In the modern day, these fields just look like normal, like regular fields that you might see. And you would not know that there's like hundreds of unhonored burials underneath your feet. We would like to learn more about these burials. However, excavation is very unethical. So that's where ground penetrating radar comes in. So how GPR works is that it sends waves down from the transmitter, right, into the subsurface. And then once it hits something, it reflects that signal back into a receiver. You can see that data through a computer console while you're working through the field. So what does that data actually look like? That data looks kind of like this. So this is a photo of some field work we did that was unrelated to the project. However, it's like black and white. There's like a lot of squiggles in it. For my point of interest in my project, I'm looking at typical diffractions. So they look kind of more like upside down parabolas or frowny faces. After that brief explanation of what they look like, I have a little activity for you guys. So in your head, I want you guys to see how many signatures you can see in this real data set. Okay, I see at least 7 when I was making the slide, right? But maybe you guys counted more, maybe you guys counted less. It's really hard to interpret because there might be like other things buried and there might be like interference with other stuff in the environment. So that's where GPR Max comes in. So GPR Max is a computer software that you can code like shapes into and create different scenarios that mimic GPR data. This is an example of code I wrote, and you can also control a bunch of variables in the software. The main models I worked with were 2D scans, and I made 6 of each scenario of different bone sections. So I had 3 long way skeleton scans. So I had a skull and a spine. I had the long arm bones. I had the long leg bones. I also had 3 short way scans. So I had one going through the skull, one going through the 2 arms and the spine, and one going through the 2 legs. And after creating that mimicked GPR data, this is what it looked like. So these long way scans, you can tell they all kind of are very similar. They kind of have like this weird M shape that is a little bit longer than a typical diffraction. And a short way scan, they have more of that typical diffraction shape that you can tell. And looking at real data, you might not be able to tell exactly what kind of bone you're looking at, but you could probably tell what direction that burial is in. So looking at real data from Alma City Cemetery, I compared it to my GPR models. So here is an example of a diffraction right here. And I think it matches up closely with this GPR data set that I've made. So I think that this is a shortwave view of the adult-sized arm and spine, and it's most likely less than half a meter deep. So why, should we care about this project, right? So this is a part of a graduate student's PhD and master's project. Shout out to Isla. This is also to honor the dead in buried Potter's Field, since there is lack of written documentation, and we can get a better gauge of how many people were actually buried in a plot. This was also my first research experience ever, so I learned the ins and outs of research and some academia aspect of it. I also had tons of fun, work hard, play hard. So here's some photos that I did outside of work and exploring the state that I was in. Thank you to everybody on this slide. And yeah, that concludes my presentation. Thank you.
Great work, Elena. Thank you. Our next presenter is Khuzema Hussain from Delaware Community College in Media, Pennsylvania. Khuzema did his project under the direction of Dr. Cynthia Lowry Birkins at Lone Star College in Conroe, Texas. His title is Can Ground Penetrating Radar Help Us Find Places Worth Looking for Fossils?
Thank you, Becky, for the introduction. Yeah, my project looks at whether ground penetrating radar, or GPR, can be used as a non-invasive way to identify subsurface features that could potentially be worth investigating for fossils. Now, the basic idea here is very simple. If you're interested in finding something underground, the traditional approach would be to eventually dig. But before you start digging everywhere, it would be useful to have some idea of where something interesting might actually be located. So that's where the GPR comes in. GPR sends electromagnetic signals into the ground and records how those signals are reflected back. Those reflections can give us information about the changes in the material beneath the surface. So my research question became, can GPR be used as a reconnaissance tool to identify subsurface anomalies that could potentially represent fossil-bearing targets? Now, for this project, we worked in the Gulf Coastal Plain of Southeast Texas around the Lone Star College Montgomery area, which is northern Houston metro area. Now, we collected GPR data at 4 different locations. The first was a control site right outside the building that I'm in right now at the Lone Star College, where a fossil sample was buried a few months ago for a different project. Now, the second was another location in the Lone Star College grounds. The third was W.G. Jones State Forest, and the fourth was Sam Houston National Forest. We chose these locations to give us a mixture of controlled and natural environments. Now, the control site gave us a known target that we could use to understand what a buried object looked like in the radar data. The college grounds gave us an accessible location for testing the equipment and developing our survey workflow. Now, the 2 forest sites were more natural sediments with relatively undisturbed sediments and geological conditions that could be useful for future paleontological investigations. Now, at the field sites, we first documented our our locations with GPS and photographs, and collected the GPR data using a 500 megahertz sensors and software snogging system. At W.G. Jones, for example, we collected a 24 by 24 grid with 2-foot line spacing. Once the data was collected, that was bought into the ECHO project, which is a software for processing the radargrams. The radargrams are the images that are generated by the GPR machine as you do conduct the survey. Now, after that, with some processing, we found the most interesting, actually trying to understand what the radiograms were showing us. Now, this is an example from the W.G. Jones State Forest grid. When you first look at these radiogram, it can honestly look a little confusing. There are a lot of different colors and reflections, and at first it's not necessarily obvious what is important. But once you start looking at the patterns, you begin to follow reflections across the profile. Now, some of these reflections are relatively continuous. Those can potentially represent changes or boundaries within the shallow subsurface, such as differences in sediments, etc. We also see some areas where those reflections become sort of disrupted, where we get more localized, higher amplitude responses. Now, these are the features that we are treating as anomalies of interest. But there is an important distinction here, and we don't necessarily say that the anomaly is necessarily a fossil. Now, a GPR response can have several possible explanations. It could be a change in sediment. It could be a change related to moisture. It could be a buried object, or it could be another natural human-made feature. So rather than saying that we found a fossil here, the more appropriate conclusion at this stage is that we identify features that may warrant further investigation. Now, why it matters? For me, one of the biggest things was learning that geophysics isn't really about pushing a button and getting an answer. There's a lot that happens before, during, and after the survey, how to lay out the survey, document the sites. This was my first research experience, and it showed me how much difference every single day makes in a research environment. And probably the most important lesson was here for the research purposes was that GPR can tell you that something is different, but it usually can't tell you exactly what the thing is by itself. And that's why field observations, geological knowledge, and eventually ground truthing are so important. I want to thank Dr. Cynthia Laurie Birkins, Lone Star College, Corbin Shaskin, who's an undergraduate student here who helped me a lot. Of course, Dr. McKean, Kelsey Drews, alumni mentors, and EarthScope staff, and more than anyone, NSF and NGF for their support. Thank you.
Thank you, Khuzema. Our next presentation is by Rachelle Reppe from the Community College of Denver in Denver, Colorado, soon to be Portland State University Honors College in Portland, Oregon. Her project was under the direction of Dr. Alex Haytem at the United States Geological Survey in Golden, Colorado. Rachel's title is Improving the Geometric Representation of Faults in the U.S. National Seismic Hazard Model.
Thank you, Becky. So to get right into it, I have been working at the USGS this summer on the U.S. National Seismic Hazard Model, which is a scientific framework that calculates earthquake frequency to estimate potential ground shaking across the country. The USGS updates this periodically, and on the top right here, you can see the most recent iteration, which was published in 2023. This is an output hazard map. The next planned iteration is for 2029, and while the 2023 version greatly increased the number of faults included in the model from about 650 to 1,017, there is room for improvement for how the subsurface fault geometry is represented. So here on the left, you can see what a fault may look like on the surface. A fault is essentially a fracture that allows blocks of rock to move relative to one another. When slip occurs on a fault, earthquakes happen, which is why it's relevant to understand. So below, they don't just dip down at one angle. If you've heard of a dip angle, there are multiple angles that they can be at, different lengths. So my project was to see if including various assumptions, which can be seen here on the figure on the right, how they influence the output, basically. So we included seismogenic depth correction, which on the right here, on the bottom right where the blue is circled, that would be a correction versus the gray dashed and dotted line. That would be the average 15 kilometers that was used in 2023. So we're saying if it's variable from fault to fault, obviously an increase, say that's not to scale, but 3 kilometers, it would increase from 15 to 18, changing our understanding. And similarly for local topography on the top left here, where the red is circled and labeled topographic correction, that would be similar in that we'd want to consider the elevation of that and how it influences the fault as well. Intersections are another factor to consider. This intersection that's labeled with the green where they intersect here, the dash is what we believe does not physically happen with faults. We don't think that they cross through each other, rather that one truncates there or basically stops where they intersect. Obviously, taking that away from the fault changes how we understand it, changes the length of it and thus the area, which I'll get into here in a moment. And then lastly, how including variable dip angles, which are labeled here at the top right, you can see that one sort of goes through to the actual fault line here going down. So including the variation, because while we have a good idea of how this works, we can't look all the way down into the earth. So accounting for all of these, the goal is to make a more precise model. How we tested this, on the top right here, you can see the seismic moment equation. The area is what we isolated as the variable. So we used a static rigidity, which you can see the scientific notation here on the slide. As well as the same slip rates from the 2023 model. So as we're looking at how the area changes with each of these geologic assumptions that I just mentioned, we're able to see how seismic moment then changes, which I'll also speak about momentarily. But basically, we have the 3D versions of these faults, and you can calculate area for them. So we started with the 2023 version, got the area for all of the faults, and then we say, okay, when you add seismogenic depth, how does this change the area not only of each fault, but the total model? And then the same with local topography and truncation where it's applicable. So only 393 of the 1,017 are truncated. So then where that's not relevant, of course, it just wouldn't apply to those faults. I used PyVista and QGIS to make various maps and graphs, which you can see some examples of here. And overall, we found that seismogenic depth had the greatest influence on the model. It increased area and moment significantly. There was another increase when local topography was added in, and there was a decrease this is what we expected to happen with the truncated faults. On the top right here, you can see a map that I made in QGIS that shows the ratio of the seismic moment change from that original 2023 version to the final version of this, and there was overall a 6.34% increase in area and 21.14%, which you can see on this graph here, that as you work through the workflow, how it influences. But 21.14% in the moment rate, that is relevant because it directly influenced the estimated geologic moment rate that comes out of the model. And the model is used for public safety planning, to establish building codes for insurance rates. There's a societal impact there as well. So if this map were to be like a lot of red, which you can see the extremes on either side, that would be an indicator of like, okay, what's happening here? But that was not the case. We saw about what we expected here, as you can see. So I would like to thank my mentor, Dr. Alex Haydum at the USGS, and her supervisor, Dr. Rich Briggs, as well as the National Science Foundation, and of course the entire EarthScope team and all of my peers. Thank you very much.
Fantastic. Thank you, Rachel. Our next presenter is Ciean Kissee from San Joaquin Delta College in Stockton, California. Ciean did her project under the direction of Dr. Ophelia George at Pensacola State College in Pensacola, Florida. Her title is "What Can Shear Wave Splitting SWS Analysis Tell Us About Mount Spur's 2004-6 Unrest Episode?"
Over the summer, we investigated what shear wave splitting analysis could tell us about Mount Spur's 2004-6 unrest episode, and Mount Spur is an ice-capped stratovolcano located in the Cook Inlet region of Alaska that stands at an elevation of over 3 kilometers tall. Between 2004-6, its summit vent experienced unusual volcanic unrest that did not result in an eruption. During this unrest, multiple summit deformation events occurred, including the formation of an ice cauldron in the summit vent, the formation of a lake in that ice cauldron, and the occurrence of multiple debris flows leading down from the summit. We applied shear wave splitting analysis to the seismic events that occurred around Mount Spur between 2004-6 to learn what subsurface processes may have interacted with these surface deformation events. A shear wave splits when it hits against an anisotropic medium, and a medium is anisotropic when it has lattice preferred orientation, changes in fracture density, or microcracks caused by magmatic activity. The shear wave splitting analysis technique we applied was a combination of Silver and Chan's minimum eigenvalue and Ando et al.'s cross-correlation analysis techniques, and was developed by Tiambi et al. We ran 1,515 event station pairs through a MATLAB implement of TMB et al.'s technique, and we derived these 1,515 event station pairs from 989 of the roughly 6,000 seismic events the Alaska Volcano Observatory identified around Mount Spur between 2004 to 6. We had to cull some events because they either weren't picked up on one of Spur's 4 3-component seismometers, lacked available data on IRIS, fell outside of our shear wave window, or had low signal to noise ratios. For each event station pair, we selected a time window around the P wave and around the S wave, and our code would return a diagnostic plot of the event station pair's splitting measurements. These measurements had to have a corrected transverse that was as close to flat as possible. The peaks of the corrected waveforms had to align. The particle motion had to transform from elliptical to roughly linear. The error surface had to have a singular bullseye. The graphs of phi and dt had to be plotted as close to horizontally as possible. The error phi could not exceed plus minus 20 degrees, and the dt could not exceed the s minus p time. This processing returned 511 acceptable splitting measurements, and as plots A and B show, the phi or fast direction and dt or delay time of the splitting measurements show no temporal or depth-dependent trends. The shallow earthquakes in our data set had a range of anisotropy values as represented by contour plot A. The shallow earthquakes also produce the highest percent anisotropy observed in the data set, and this high percent anisotropy had a correlation to events that were detected between June 2004 and June 2005. Contour plot B represents deeper earthquakes in our data set, and these deeper earthquakes had a low percent anisotropy throughout the unrest period. Our depth anisotropy pattern is consistent with a anisotropic volume who is more associated with the hydrothermal magmatic system beneath Mount Spur rather than being caused by station side effects. Our results also indicate stress-induced fracturing occurred, which is typically accompanies magma and or volatile intrusion. Increased shallow permeability may have also been the facilitator for the observed summit deformation, and our interpretation was limited by asymmetric station geometry, path integrated splitting measurements, and sparse ray path coverage north of the summit vent. Overall, our study demonstrated how shear wave splitting measurements could contribute to comparative assessments of subsurface processes. I would like to thank my mentor, Dr. Ophelia George, for helping me through this experience, and also the Geo-Launchpad and EarthScope Consortium mentors I had when they helped me through this. Yeah.
Hey, great job, Ciean. Thank you. Our next presentation is by Nicolas Hausner from the Community College of Denver in Denver, Colorado. His project was under the direction of Dr. Virginia McLemore at the New Mexico Bureau of Geology and Mineral Resources and the New Mexico Institute of Mining and Technology in Socorro, New Mexico. His title is Critical Minerals in New Mexico.
All right, can you hear me? Can you hear me?
We can. Yeah.
Okay, awesome. All right, so my project is Critical Minerals in New Mexico. So critical minerals refers to earth elements that we mine, which are important to the United States economy. They are important to national security, and they're mostly imported from other countries, which means their supply chains are vulnerable to disruption. There are about 60 critical minerals as defined by the U.S. Department of Energy, which comprises roughly half of the periodic table of elements, as you can see marked blue on the table on the right. So I studied the presence of critical minerals in southwest New Mexico in the Steeple Rock Mining District, which has been mined continuously since the 1880s, which means there are a lot of closed mines, but these mines are still privately owned, and there's an interest in reopening some of them in the search for critical minerals. So you can see my study location there on the far right, outlined in that red circle, which is right by the Arizona border and near the New Mexico boot heel, with the border with Mexico. So the need for many minerals will skyrocket to supply the future of technology, such as for data centers and also for renewable energy sources, such as solar panels and wind turbines. And also national defense creates a large demand for uh, minerals. And since critical minerals tie into the national security of the country, uh, national defense, these materials needed to manufacture jets and other items for national defense make some of these minerals very important. And then also the production of batteries requires many critical minerals, um, such as for electric cars and electricity storage. So my research question and methods. My research question is, do rock samples from Steeple Rock Mining District indicate valuable critical mineral presence? So I started with sample collection in the Steeple Rock Mining District. You can see a picture of me there in an active mine, uh, chipping away at some amethyst in the mine. And then my next step was sample selection, choosing which rocks were most interesting to look at. And then I made them into slabs with the rock saw so that I could further identify points of interest, as you can see with that slab of amethyst there. And then my next step was preparation of those small points of interest so that I could further analyze what was in the rocks. And so my methods went beyond just looking through the microscope, though. I also used X-ray diffraction to identify some minerals that I couldn't identify just uh, through the microscope. I also used whole rock geochemistry data that was already available so that I could be better informed about what my results meant. And then also I used petrography, which is uh, looking through the microscope and such to identify what minerals were present. And then uh, another big method for my project was using the electron microprobe, which details very, very small points and the chemistry behind them. So I was studying mineralogy for my project, and I was connecting critical minerals to sulfide minerals, which sulfide minerals are formed by metals bonding with sulfur to make metallic looking minerals. And so you can see there's galena in the bottom left, which is a lead sulfide. And I had a lot of galena in my samples, which I thought was pretty cool. And so you can see I circled some points where there were galena in my samples. And then you can see on the right an example of how I cut those out to much smaller pieces and polished them down for further analysis. So my conclusions are that there's a high amount of silver within covellite in my samples, which is a copper sulfide. And so silver and copper are both critical minerals. So finding the presence of these two critical minerals together is very important. The covellite was up to averaged around 5,000 parts per million, which is very significant, although my samples aren't full of covellite. So further analysis would be needed to determine just how much covellite is present in in this mining district. And then also, my results indicated the presence of tellurium within galena, which tellurium is a very rare earth element. And so finding the presence of any tellurium is very significant, but the cost of processing it is very high. So this result is likely less significant than finding silver within covellite. And you can see here on the right is a picture from the electron microprobe with all my points of analysis that are these very microscopic points where I could get all these weight percentages. So thank you for listening to my presentation. I'd like to thank everyone at EarthScope for helping me out through all this, and then also to Dr. Virginia McLemore, my mentor, Dr. Nels Iverson, Samantha Beauchesne, and the economic geology team uh, at the New Mexico Institute of Mining and Technology. Yeah, thank you.
Thank you, Nicholas. Our final Geo-Launchpad presentation is by Jasmine Bruns from Santa Barbara City College in Santa Barbara, California, soon to be the University of California, Berkeley. Jasmine's project was under the direction of Dr. Anant Haraharan at Scripps Institution of Oceanography in La Jolla, California. Her title is Using Surface Wave Arrival Angle Anomalies to Study Upper Mantle Structure Beneath Yellowstone.
Sorry. Hello. Yes, so this is where I worked this summer, at Scripps. And we all know that Yellowstone is a supervolcano, but the geometry of the structure and anomaly beneath the Yellowstone and Snake River Plain is still debated. So down here on figure 1, you could see different modeling methods that have been used to image Yellowstone. This is the Snake River Plain, and this is the Yellowstone caldera. And you could see that there's a lot of imaging that's been done, but there's still not a lot of agreement between all of the different models. So it was my job to use a unique way to approach this by using surface wave arrival angles to better constrain the anomaly beneath Yellowstone, which is something that hasn't been done before. And I did this by clustering earthquakes in different source locations, mostly in the Southwest Pacific, and that were recorded by the US Array, which is this the US in blue, and then the red is all the earthquakes that were in my data set. And I measured the arrival angles from the travel times of those earthquakes using a mini array approach, which is illustrated in this figure, where we basically find the direction that's most consistent with the way the travel times change across the stations. And yeah, and I do this and I create arrival angle composite maps to generate observations. But first, this is an example of what diffraction pattern looks like when a surface wave interacts with a low velocity anomaly. It creates this like fringed pattern of red and blue striped like pattern due to a diffractor. And so knowing that, I implemented my data from these different clusters of earthquakes in different locations, and I created composite arrival angle maps for each cluster that I did at different periods. And you can see clearly that there's a diffraction pattern of that red and blue streak. And these are just from observation, so we knew that something was going on where the Yellowstone anomaly is located. Also, it's interesting to see at different periods how the wavefront changes and how we can study the diffractor at different depths. So I modeled my observations by solving for the best fitting model. These are the same observations on the previous slide, but I performed a grid search over the whole model space, and then I varied the latitude and longitude of the diffractor, the width, and the tau max to generate thousands of synthetic diffraction patterns and predictions. And you can see for this specific observation, this is my best fitting prediction. And then I also implemented a misfit code to solve for the least misfit for the diffractor position, for the diffractor width, and the strength of the anomaly. So you could see that the dark blue is the least misfit, and that's where the diffractor is located for this specific observation, and same with the width. And I do this for all of my observations. This is just an example of one, but it helps us see how the wave field interacts with Yellowstone from multiple different locations and how we can get really good constraints on the actual geometry of Yellowstone. And this is really important because it complements traditional seismic imaging and helps us like truly infer its structure in future projects. And this project was really important to me because I learned how to code in MATLAB and I learned why and how we study Earth structure using different methods. And I read a lot of papers and learned how to engage with scientific literature in a very meaningful way. And it taught me a lot about how research is done in academia. And I'm excited to continue my research at Berkeley next semester and writing my paper. So I just want to give a big thanks to EarthScope and to my mentors, Anat and Gabby.
Fantastic work, Geo-Launchpad. Way to go. Fantastic. All right, we'll have a little bit of time, about 10 minutes for a Q&A. So I see one question in the chat already, so I will start there. Feel free to type more questions into the chat or raise your hand if you'd like to ask your question out loud. And we'll try to kind of direct them to whoever might be best at answering them. If you can associate a name with it, that would be great. So we have a question from Christine about GPR, and I think, Nick, maybe prepare yourself because I remember you talking about the 3D plot question. So
Yeah, for
do you
sure.
mind answering? It says, what kind of resolution does GPR have and to what depth? How much variation was there in the study sites, soil layers, and rock layers? Did any one of the interns get to the point of making 3D plots of surfaces reflectors? So I know you can at least answer
Totally.
that last question.
Oh yeah, so I can break that down into a section. So for resolution, GPR, there's lots of different variables for it. So with antenna, typically the like 400, 500 megahertz, you get deeper images, but with less resolution. In Kansas, it all also depends on the soil type. So in Kansas, there's a lot of clay, which is very dense. There's not a lot of airspace in between for the waves to go down through. So you don't really get as deep as like in sand, for example, where you get 30, 50, I think even up to 100 meters down, which is insane when you think about it. And then how much variation was there in our study sites? For us in cemeteries, there's not that much variation. I mean, in the soil itself, it's not very deep. The bedrock is, I believe, like 2 to 3 meters deep. Um, and then we weren't actually looking at the geologic layers, so we didn't have a need to go further than that. But I'm sure others who use the GPR might have a different answer. And then did we get to the point of making 3D plots for our surfaces of reflectors? I'm not sure if you mean our models or the actual GPR data. For GPR data, the 3D models are mostly used for like looking at where does the bedrock end, if we're looking for like mining or like groundwater, those kind of purposes. So we didn't make any 3D models for this base project. And then when the GPR is passing over it, you do end up getting a flat image of like a 2D scan. So making a 3D model would make it easier to run those scans over it, but it doesn't necessarily produce a 3D result graph. I hope that helped.
Thanks for
Thank
taking
you.
that question, Nick. So we have another question who I believe is for Jasmine. What are the depth ranges imaged for the surface wave diffraction study?
That's a good question. We we used different periods of like I'm not exactly sure the depth ranges. I know that like we had like 30-second periods to 100 seconds, and like once you get to 100-second periods, you see way deeper crust, but we never, or at least I never like I didn't know the exact answer to how deep the crust was at that point. But I can ask my mentor. Sorry.
Thanks, Jasmine. No, that's fine. Thanks, Jasmine. Okay, we have a question from Donna, and you all can decide, Geo-Launchpad, who would like to answer this question. Maybe not Nick or Jasmine because they've answered a question already. So one of the five of you. What was the most surprising or unexpected thing that happened for you this summer as you worked on your project? Does anybody want to take it?
I will.
Rachel?
Yeah.
Yeah.
For me, there were a couple of things. One, when I was introduced to the project, I was just like, I don't know if I can do that. But also how humble and helpful everyone at the USGS is. I was really nervous because you get a bunch of clearance to enter and stuff, and I was like, this is gonna be I don't know what it's gonna be like, but everyone is just as nice as you could possibly imagine. So it made it easier for the stuff I struggled a little bit without having experience in, to get there. And then looking back at the project, I'm like, I would have been surprised 2 months ago to see how everything wrapped up. So for me, that was the best part. And EarthScope. I think I didn't know when I got into this program how much support we would have and how much we would get from this program beyond the internship. So it just really came together in an awesome way, from my perspective.
Great. Thanks, Rachelle. I just want to say, I think that's often a misconception is that scientists are these people up on a pedestal or whatever, and they're really just geeks that like to study. And so I totally understand. I back in the day in the same boat. It can be very intimidating.
Khuzema, go ahead.
Yeah, I just want to add to that and say that even during orientation, we were talking about imposter syndrome, and all of us were in that boat at the time where we were like, okay, we are here, we got here, maybe by pure luck, chance, or whatever it was, but we are here. But now going forward, how is it gonna be? And yeah, it's an amazing journey that we've been a part of here, and thanks to everyone. Yeah, everyone involved. You all have done a great job, amazing job in preparing us to even get to this point. So yeah.
Thanks, Khuzema. You all have done a fantastic job, and you did not get here by chance. Donna highlighted it in the chat. Competitive. It's a very competitive program. You earned it. Does anyone else want to take the surprising question? What was unexpected or surprising?
I can share a quick tidbit. For me personally, the craziest part was going across the country and just living in a different state. I'm from Virginia, and I feel very blessed to have traveled, but I've never actually lived outside of the East Coast. So being in the dead middle was definitely a little bit of a culture shock. There are, in fact, tornadoes. We don't have tornadoes where I'm from. So on my very first night, there was a tornado siren, which was quite alarming. I survived, thank goodness. But yeah, just being in a totally different environment was honestly the craziest part, and not having all these mountains around us. It's very flat, all the grasslands.
It's a good one. All right, one more call. Anyone? We haven't heard from Elena, Ciean, or Nicolas. Do any of you want to tackle? Nicolas, go for it.
Yeah, I have something to say. I was very surprised by all the collaboration, somewhat similar to Rachel. Uh, After getting here in Socorro and finding out how much collaboration I was having with all these other graduate students and other professors that were helping me out with my project was amazing. You know, since from the beginning I knew the name of my mentor and everything, I sort of envisioned it being more of a one-on-one project, but I was very amazed by all the people that were willing and happy to help me out with my project and help me get things done on time.
Thanks, Nicolas. All right, we have another question from Christopher, and I think this is for Jasmine again because it references the Yellowstone anomaly. How did you quantify the uncertainty of your measurements of the shape of the Yellowstone anomaly?
Yeah. Well, when I was generating my composite arrival angle maps, I also generated the uncertainty of each station that took in the arrival angles. But when I calculated my misfit function, it allows me to quantify the uncertainties. So there was a 95 to 99% confidence interval that corresponds to the model that I used on my model. So yeah. I don't know if that explains.
That's great. All right, I think for today we will go ahead and wrap it up, but I do want the interns to be looking at the chat. There's a lot of positive comments in there, so make sure you read those. We do have 2 more sessions of internship presentations coming up, so we hope that you'll consider attending those and supporting those interns as well. We have our Recess Summer Internship Program, which has a summer research spotlight later on this afternoon. And tomorrow we have our student career interns presenting in their summer showcase as well, so please consider attending. For now, if you have questions, feel free to reach out to me or our internships team email. Thank you, everyone, for attending and supporting our Geo-Launchpad interns. Please go ahead and give them one more collective round of applause in our emoji feature in Zoom. So great job, everyone. Thank you so much.